Okay, so today I'm going to talk about the random incident problem, i.e. the man waiting for a bus, so what's the average waiting time of a man waiting for a bus. So let's see a easier version, which means the bus does not arrive as a Poisson process, but as a, like we said, the bus only arrives with two cases. So here's the bus station. The bus only arrives with two cases. Either it arrives each 5 minutes or it arrive at 10 minutes randomly. So, and we assume the PDF of this is equal to a half and a half with x equal to 5 and x equal to 10. So, one might think that the expected waiting time of each one is you either arrive at 5 or either arrive at 10. If that's the case, the expected time, waiting time. Because this is the wrong version, I will make the quote mark. It's either we arrive at 5, which means we arrive at the middle, because you know it's uniform distributed. So it's a half times 5, but you arrive at the middle, so times a half again, plus a half times 10 times a half again is equal to what? It's equal to 415. But we know this is not true, right? Because from what you see, when you arrive at 5 or arrive at 10, it's not equally distributed because it's a timeline. So there is more possibility for you to arrive at 10. So this is the wrong answer. So what's the right answer? The right way instead should be, there are two cases. The case one is you arrive in the 5 minutes interval. And the case 2 is you arrive in the 10 minutes interval. And what's the probability of that? So you know 5 or 10, you consider as a whole is 15 minutes. So the case 1, you have the probability of 5 divided by 15 is equal to 1/3. And the case 2 is equal to 10 divided by 15 is 2/3. So here we see that actually the expected waiting time, the true expected waiting time, is equal to a half, 1/3 times 5 times a half. Because when you arrive in this interval, you will assume you arrive at the middle because it's uniform distributed. Plus 1/3, 2/3 times 10 times a half. And here, which is equal to 6 and 25. And we notice that this number is larger than the number we had before, which is 15/4. You can check that. So this is like a baby version of the random incidence problem. And we notice that you actually don't have the average of these two cases, but the longer you have the interval, the more possibility you will arrive in that interval. So let's do the real cases in the book, which is you have a bus station, and the bus arrive with Poisson process. And here, lambda is equal to 0.1 per minute, which means 10 minutes average arrival time. Right? Because lambda is equal to 0.1 per minute, so 1 divided by, because since expected value of this x is equal to 1 over x is equal to 10. It's 10 minutes, right? Which makes sense. And, 10 minutes average arrival time. And here, we want to know the random incidence, which means I'm waiting for the bus. So what's my average waiting time? Which means I have a timeline, and this time you have the average of 10 minutes, but it might be 5 minutes 20 minutes, 7 minutes, 30 minutes, 3 minutes, etc. Right? And there's more possibility to arrive at those longer interval. That's the key of this thing. So we have another name which is called the random incidence paradox. Because essentially you will see the answer, that is, you need to wait for 10 minutes and the bus will arrive 10 minutes before, which seems like you have a 30 minutes average, but actually it's 10 minutes. So let me show you why. So first, let's denote the interval you arrive at the bus station as W. So here we have so many intervals, so let me go back. So for those intervals, maybe I'll give it the name which means y1, y2, y3. This is those intervals that I don't know if I arrive or not. But once I arrive it at some random time, then that interval is what we call the W. We don't call it a Y anymore. I will explain that later. And now let's find out what's this PDF of this W. So we want to find out the PDF of this W. Firstly, like I showed you in the first example, this W will have the PDF that is proportional to its length, right? Which means this W, when you have arrival at that given time, will be larger probability when you have the longer interval, which means this W will proportion to the length times the initial PDF of this W. And we also know that the integral of this fyw must equal to 1, and we also know the integral of this fyw is equal to 1, right? Because this is a PDF, you integrate any PDF is equal to 1. And the integrand should be from 0 to infinity. And in these cases, we will know that in order to have this integral of the w is also equal to 1. So here it's proportional, which means it's proportion to a constant. So we know w is equal to a constant times w times fyw, where this constant must equal to the expectation of this thing, which is equal to 1 over expectation of this y times w times fyw. So that is a story. And then what we want to do is find out what's the expectation of this w, right? Because now we know the PDF. So expectation of this w is equal to integral of w times f. Maybe I use another notation, it's easier to see. Maybe you'll use x, fx, dx, 0 to infinity. And we'll replace this x is equal to integral of 0 to infinity, x will replace by that. Notice here the expectation of y is a constant. And here w is x everywhere times f x dx. This is equal to what? This is equal to x squared times that. So we take this out. And what's left with integral 0 to infinity x squared fy x dx. And we notice here is just expectation of y, and in the integral is just expectation of y squared. That's the expectation of this w. And we will check it quickly that in this case the expectation of waiting time is 10 minutes, right? And here the expectation of this thing is equal to 2 divided by lambda squared 0.1 squared, and which will give us 20 minutes. You can check it by yourself, which makes sense because when we arrive at this bus station, it's not average 10 minutes, but we will most likely to arrive at a longer interval, which is actually 20 minutes. And now let's have this picture. Suppose this is our w. This is the interval we arrive. This is the time we arrive. T star is the arrival time of the passenger. And we will give you one more notation. That is something we'll introduce here is S and R. And we'll give you the name of this, so two things. So S is the interval of the last bus arrival to passenger arrival. This S does not have a name, so we'll just call it S. But then this R is also an interval. It's an interval that the passenger waiting time until next bus arrive. And this R will have a name. This R, usually you will see some paper we call it the residue time for this R. And this R is also the answer we want to know in these cases. And I don't want to do a derivation of that. When you have a Poisson process, the arriving time will be uniform distributed. So we know now is W is equal to 20 minutes. Then you will arrive in this interval even distributed. So the R will equal to 10 minutes. So essentially it means R will arrive here. So the S will also equal to 10 minutes. And that gives us the answer for that question. This is a question in the page 90 of the book. So maybe one more thing. This residual time is actually, we have another distribution we call the Erlang distribution. I'm sorry, the W. So the W will follow the Erlang distribution, which means W is follows the Erlang distribution when the lambda is equal to 2 of order 2, which means it's the sum of two exponential distribution. So you can check for the definition of the Erlang distribution, and I think